The big shift is this: science is not only about what we know, but about how we know it. This year, we trace the path from a question to a trusted answer through observation, measurement, modeling, and testing.
Meet a scientist, Meghnad Saha. When studying a light from stars, Saha did not try to model every atom or reaction. Saha, honored on an Indian postage stamp, faced an impossibly complex system, an entire star. His genius was in deciding what to leave out, exactly the skill we've been practicing. Saha's simplification. He treated the matter in a star as a hot gas, ignored many complex processes, and focused only on temperature, pressure, and how atoms form ions. By stripping the problem down to just a few key quantities, he turned an overwhelming system into one he could actually describe with equations. This is model building at the highest level. Saha's result. This simplification let him explain how the color of a star is deeply connected to its temperature. From his simplified model came a powerful, testable result we still use today. It shows that a well-chosen simplification isn't a shortcut that loses truth. It can lead to real, lasting discoveries. Science uses language precisely. As you go deeper, you notice science uses words in a very careful, precise way. In everyday speech, we're loose with words and still understand each other, but science can't afford that confusion. The same word must mean the same thing to everyone who reads it. Everyday words, special meanings. Words like force, work, cell, and reaction mean something very specific in science. In daily life, force might mean effort or pressure, but in physics, it has one exact meaning. Students need to learn to switch from the casual meaning to the precise scientific one. Why precision matters. Precise meanings let scientists communicate clearly and unambiguously anywhere in the world. If reaction meant different things to different people, experiments could never be fairly compared. Precise definitions let a result found in one lab be understood and trusted in another. A shared language. Science uses a shared language of agreed terms, symbols, and units so people can compare results and build ideas together. Think of it as a global agreement. Everyone uses the same words, symbols, and units so their work fits together like pieces of one puzzle. Science is a team effort across countries and generations. Symbols and units. Quantities like mass, velocity, force, and current are written as m, v, f, and I, each tied to a defined unit. The symbol is shorthand for the quantity, and the unit tells us how it is measured: kilograms for m, meters per second for v. Symbol and unit always travel together. A number without a unit is meaningless. Mathematics as a language. Science turns to mathematics, so relationships between quantities can be stated clearly and tested carefully. Maths lets us state a relationship so exactly that it can be checked against real measurements. It's the most precise language we have for describing how the world behaves. An equation is a statement. An equation is not just a calculation tool. It is a compact statement about how things are related. For example, distance, time, velocity. Read an equation as a sentence. V equals d divided by t says that speed is distance shared over time. Once you read it that way, you can use it to predict where something will be at a later moment. Math is not memorizing. Understand the situation first, identify the relevant quantities, then use the relationship to reason. Math becomes a tool for thinking. The trap is treating maths as blind formula plugging. The real method is to picture the situation, spot the quantities that matter, and let the equation guide your reasoning. Done this way, equations feel less like obstacles and more like helpful guides. Ask the class, how can an equation be a sentence rather than a sum? Threads of curiosity. Why light is C. The symbol C comes from the Latin celeritas, speed. The speed of light is a defined constant, exactly 299,792,458 meters per second. Symbols often carry history rather than being simple abbreviations of convenience. And because the speed of light is fixed by definition, it's one of the rock-solid constants the rest of physics is built upon. Ready to go beyond. The fuel disaster. A plane needed 22,300 kilograms of fuel, but the crew used the density in pounds per liter instead of kilograms per liter. A pound and a kilogram are very different masses, so the wrong density gave a badly wrong fuel figure. This is a true story showing that units are not a small detail. They can be a matter of life and death. The fuel lesson. The aircraft was about 15,000 liters short and glided to an emergency landing. The plane was damaged, but luckily, there were no casualties. Using standard SI units everywhere removes a whole class of dangerous conversion errors. The simple rule? Stick to one agreed system of units. Why a kilogram is universal. A kilogram means the same everywhere because measurements use agreed international standards, not local objects or opinions. This is why a vegetable seller's weight is honest, and a scientist's measurement is trustworthy. Shared standards protect both everyday fairness in trade and scientific accuracy in the lab. Laws, theories, and predictions. Organizing our knowledge. As observations repeat and ideas are tested, we organize understanding using laws, theories, and principles. These three words sound similar but mean different things in science. Knowing the difference helps students use them correctly instead of treating them as interchangeable. A law. A law describes a regular pattern in nature, often in words or maths. For example, Newton's laws explain the jerk you feel when a bus stops suddenly. A law tells us what regularly happens, usually as a neat rule or formula, but it doesn't explain the cause. When the bus stops, your body keeps moving forward. That's a law of motion in action. A theory. A theory goes further and explains why the pattern happens, based on evidence. For example, atomic theory explains how molecules form. A theory answers the deeper why question and is backed by lots of evidence gathered over time. That's why atomic theory can explain a huge range of chemical facts all at once. A principle. A principle is a broad idea that helps us make sense of a situation. For example, conservation of energy when climbing stairs. A principle is a wide idea that applies across many different situations. Conservation of energy doesn't describe one single event. It's a rule we trust everywhere, from climbing stairs to powering a whole city. Theory is not a guess. In science, a theory is not an untested idea. It is an explanation built on careful testing and critical examination. This is a crucial correction. In everyday talk, it's just a theory means a wild guess. But in science, A theory is among the strongest kinds of knowledge, supported by years of evidence. Open to correction. Scientific ideas stay open to improvement and change with new evidence. This openness is exactly what makes science reliable. It sounds backwards, but science is trustworthy because it can be corrected. Any idea may be improved when better evidence arrives, so the ideas that survive have been tested again and again. The power of prediction. Well-established laws, theories, and models let us anticipate what will happen in new conditions, sometimes even without doing the experiment. This is one of science's most impressive powers. Solid theories let us say what will happen in a brand new situation, guiding everything from spacecraft launches to weather warnings. Prediction examples. How far a kicked football travels, how much CO2 a reaction makes, how soft a bread bakes, how breathing changes while running. Notice the predictions come from every branch: physics, chemistry, and biology. In each case, established knowledge lets us forecast an outcome before it actually happens. Predictions are reasoned. These are not guesses. They are reasoned expectations based on evidence and careful thinking. A guess is a shot in the dark. A prediction is built on reasons and past patterns. That's why a scientific prediction can be defended and explained, while a guess cannot. Match versus mismatch. When a prediction matches observation, confidence grows. When it doesn't, scientists re-examine their assumptions, models, or measurements. A mismatch is not a failure. It's a clue. It tells scientists that something in their thinking needs fixing, and that is often exactly how the biggest discoveries begin. Example 1.2. Testable rain. Varsha says it will rain because clouds look dark. Good testable questions ask for measurable evidence and past patterns, humidity, wind, temperature trends, not yes-no guesses. The trick is turning a vague claim into something measurable. Asking, "What was the humidity last time it rained?" gives data we can actually check against, and that is what makes a claim genuinely scientific. Why forecasts go wrong. Weather depends on many changing factors: temperature, pressure, humidity, and wind, and tiny differences grow over time. A small error today can snowball into a big error next week. This is why a chance of rain tomorrow is fairly reliable, but a forecast 3 weeks out is not. Theories have limits. Even very successful theories can fail when new conditions are explored or measurements get more precise. No theory covers absolutely everything. As scientists push into new situations or measure more carefully, they sometimes find the edges where an old theory starts to break down. Failure is a strength. Science changes ideas only on evidence, never on opinion or belief. No theory is final or beyond question. When a theory fails, science doesn't cling to it out of pride. It follows the evidence. This honesty, the readiness to be corrected by nature itself, is exactly what makes science so powerful and reliable. Thinking like a scientist. Debunking myths. The eclipse claim. Food becomes harmful during an eclipse fails simple scientific questions. An eclipse is just shadow play. The way to bust a myth is to ask testable questions. Does the temperature change? Does any chemical reaction occur? Does food go bad just by sitting in a shadow? Since nothing physically changes the food, the claim collapses. It's a perfect model of scientific thinking applied to everyday life. The estimation habit. Understand the situation. Identify the quantities that matter. Make a rough estimate to check if an answer makes sense. Science values careful reasoning over exact numbers. A rough estimate is a quick sanity check. It tells you whether an answer is even possible before you do precise maths. Learning to estimate builds intuition and helps you catch big mistakes early. Estimation in action. Estimate rice to feed a family for a month, or the air you breathe in a day. Walk students through the breathing example. About 20,000 breaths a day, times roughly half a liter each, approximately 10,000 liters of air. Example 1.3. The point isn't the exact figure, but checking it's sensible. Not 10 liters, not a million. Ask the class. Name one case needing an exact value, and one where an estimate is enough. Science has no real borders. Physics, chemistry, biology, and earth science are human-made divisions, created only to help us organize knowledge. Nature doesn't come in subjects. Real problems, climate change, new medicines, even a simple face mask, need several branches working together. A mask draws on physics, chemistry, biology, and maths at once. Science is human. Above all, science is a human story of curiosity, creativity, collaboration, and questioning that grows by learning from mistakes across cultures and generations. Even if you never become a scientist, thinking this way helps you judge information and make sense of the world around you. Close the lesson. Explore through the magnifying glass of evidence, guided by the compass of curiosity. Happy exploring!
The big shift is this. Science is not only about what we know, but about how we know it. This year, we trace the path from a question to a trusted answer, through observation, measurement, modeling, and testing.
Welcome to your CBS teacher. Learn thus, explore with us, and grow with confidence. Visit rehanstudio.com.